In this video, I'm going to be talking about how the underlying bonding that a substance uses affects the properties that the substance has. So this will be kind of a review of the different types of bondings, and also we'll introduce a few new types of bondings also. The first type of bonding that I want to talk about is metallic, which, as the name implies, is used between metal atoms. It works because the core of the metal atoms do not hold on to their valence electrons very strongly. So that leads to a sea of electrons that surrounds the metal atoms. And the cores of the atoms are attracted to the sea of electrons. And that's what binds everything together. Uh, because of the way they bond together, metals are very good conductors of electricity and heat. The electricity one is very easy to understand because you have, if you put the metals into a field where you have a negative on one side and a positive on the other, those free electrons very easily move through that sea from one end of the metal to the other side. For heat, heat moves very well through the metals because as those electrons move, they can carry with them kinetic energy, and that kinetic energy as they move can cause atoms to vibrate more, and that's in essence what temperature is just the vibration of atoms. Metals are also very malleable, which means that and also ductile, which means that they will bend or can also be drawn into wires. And that happens because one metal atom does not care what other atom it is next to. So if you pull on them, they don't come apart, but they can slide past each other very easily. Or if you hit them, like with a force, like with a red arrow, they will dent in very easily. The melting point and boiling point will depend as the attraction between the atoms and the sea of electrons gets stronger. The melting point and the boiling point will go up. The next type of bonding is ionic, which is metal ions with nonmetal ions, or also could be between those ions and polyatomic ions as well. It works because ions being positively and negatively charged are attracted to each other. The opposites, positives and negatives, are attracted. Ionic bonds are very strong, so ionic bonded substances have very high melting points. They're also very brittle. If I was to hit this solid over here, if I was to hit it so that the negative chloride ion here was to shift over, this, like let's say this whole face was to shift over, so now I have a negative ion next to a negative ion and a positive ion next to a positive ion, rather than being attracted together, the entire thing would repel that face, and so it would split apart. So you cannot really bend an ionic substance. If you have these ions free to move in a liquid, such as if you melt the ionic substance, or if you put it into a table, or if you put it into, like, say, water, which will dissolve it, then the resulting liquid will be able to conduct electricity. The next type of bonding is covalent bonding, and this happens between nonmetal atoms, and it happens because the atoms share electrons between them to put them into a more stable configuration. Covalent is a little bit different than the other types of bonding because you have very different properties depending on exactly what we're talking about. Because the atoms are bonded into molecules, the type of molecule determines the properties, because we're not affecting like how atoms are stuck together when we're doing things like melting and boiling them or trying to bend them, but we're affecting how the molecules are held together. So it depends on if you have a polar or a nonpolar molecule, which we'll get into. There are some cases, though, where instead of making molecules, you make big networks of covalently bonded atoms. A classic example is diamond, where you have all the atoms are essentially held together into one big network. So if I look at one carbon atom up here on the right, it's attached to four others, and those are again attached to four others, and those are attached to four others, and so on and so on. These covalent bonds are very strong, so this makes the diamond very hard, or anything that's a covalent network, a very hard substance, very hard to be scratched. But if you hit them hard enough, if you cause those bonds to break, then you're essentially just going to shatter whatever it is. If I compare that to graphite, graphite's a little bit different than diamond. It's again just made out of carbon atoms, but here each carbon atom is only covalently bonded to 3 rather than 4 atoms, and it makes sheets, and those sheets are then held together by other types of forces that are weaker. And so graphite, like in your pencil, one layer will slip off very easily as you're writing because these sheets can come apart very easily, even though the sheets themselves are very strong. The next type of bonding I want to talk about is it's called dipole-dipole, and this occurs between polar molecules. Basically, in a polar molecule, as you've seen in the simulations done in class, polar molecules have a positive and a negative end to them. So then, just like in ionic bonding, the positive part of one molecule is attracted to the negative part of another molecule. Polar molecules can dissolve other polar molecules because they have similar attractions between them. In some cases, a polar molecule, a very polar molecule, can dissolve ionic compounds. If you have polar molecules, their melting points and boiling points will vary with bond strengths, and they will make brittle substances. There's a special case of this called hydrogen bonding. When you have hydrogen with the elements nitrogen, oxygen, and fluorine, it makes a bond that is particularly polar. Not only that, but since the hydrogen atom is so small, the positive end of it is exposed a lot and is easily attracted then to the negative end of the molecule. So this leads to very strong interactions between molecules that have hydrogen bonding. The classic example of this is water. Because water just has hydrogen bonding and not simply dipole-dipole interactions, water is actually liquid at room temperature, whereas similarly sized molecules that are polar are always gases at room temperature. And so this is very important to life on this planet because if water didn't have hydrogen bonds, it would be a gas at the temperatures typical on the Earth, and you wouldn't be able to have life as we know it. It's also hydrogen bonding is important for why water expands as it freezes, and you couldn't have ice on top of lakes without hydrogen bonding. And there's a few other examples where hydrogen bonding is really important to life and to the way a lot of things work with water. Another type of bonding, or actually the last type we'll be talking about, are called London dispersion forces. Everything can use London dispersion forces, but it's really important when looking at noble gases or other uncharged atoms and then nonpolar molecules. It works because you have an attraction between temporary dipoles. So if you look at the picture here, this would be a helium atom and another helium atom. Because electrons could spend, more time on one side of the atom than the atom itself gets a partial negative and a partial positive side to it, and that will then be attracted to the partial negative and partial positive side of the other one. Because these dipoles are temporary, this leads to a fairly weak interaction because it's kind of like turning on and off all the time. But as you get more electrons, the ability for them to be temporarily polarized gets easier, and so the London dispersion forces does increase and become stronger with more electrons. Characteristic properties: nonpolar molecules only dissolve in other nonpolar molecules. They do not dissolve well in polar molecules. So if we look at the old adage, oil and water don't mix, it's because of the different types of intermolecular bonding that oil and water utilize. The melting points are dependent on bond strength, so as we get more electrons in the system, the boiling points and melting points increase. Generally, though, if you look at a nonpolar substance, its melting point and boiling point is going to be lower than a similar polar substance, just because these are weaker bonds. Because of the way the temporary dipoles work, which molecule is next to which molecule isn't going to matter so much. And so solids are generally very malleable. Kind of a classic solid to think of that uses London dispersion forces is wax. And you can think of how soft wax is. And it doesn't completely, not super flexible, but there is a little bit of flexibility, or that you can, or denting that can be done without completely destroying it. So not completely malleable necessarily, as much so as a metal, can break a little bit easier. But again, a lot of that's that weaker attraction between things than the metals would have with each other. So this is all the different types of bonding that we'll talk about, and we'll be doing a lab where you'll be looking at different substances and classifying what type of bonding they have based on the properties they have. So it's important to have this background information before doing this lab.